What fraction of the original carbon-14 remains in a sample after 11,460 years? You do need a piece of information. You need the piece of information that the half-life of carbon-14 is 5,730 years.
11,460 divided by 5,730.
The number 2 tells us what?
You put it into the exponent of the
So if you're going to use method number 1 for problem solving on this one, here's our equation. Where y equals what? What does y represent?
14,000, 1,000, 11,460.
What does the variable y stand for? Put it that way.
How much of the radioactive thing, like substance, will be left?
So y is the percent remaining, and x equals
Number of half-lives.
So in step 1 of problem solving, we determined that there were 2 half-lives that passed. To determine the amount that remains, we simply sub 2 half-lives in for x, and we end up with 1 over 2 to the 2, which is the same as 1/4. This is convenient because the question says specifically what fraction. It does not ask for what percent. If it said what percent, what do we have to do next? Convert that to your decimal. So the decimal is 0.25. Then we convert that by multiplying it by 100, and we end up with what percent? 25%. That's method 1 of solving this problem. Method 2 of solving this problem starts with the exact same step 1. But some of you look at the equation and you're like, ugh. You don't like equations. That's fine. So for you, I encourage you to learn this and know it by heart. Exact same information as that equation. Precisely the same. But this time we simply take our 2 from right here, 2 half-lives, find the 2 on the graph, find where it intersects, find its intersection with the y-axis, and we find out that there is 1/4 remaining. So for those of you who have dedicated yourselves to memorizing the graph rather than the equation, simple way to remember the graph. On the x-axis, it's just whole numbers, 1, 2, 3, 4, 5. On the y-axis, the highest we go is 1, because you can never go above 100%, right? I know, everybody's all like, oh, 110% effort. That doesn't actually exist. It's not like a thing. It's 100%. You start at 1, and then you just always cut it in half. So 1 half, half of a half is a quarter, half of that is an eighth, and you just keep going down by halves. Where do you start your line then if you're going to draw it on? Well, we always start at 1 and 0. So if you want to memorize the graph, that's fine. Or you can use the equation. Don't care what you do. See how we arrived there? We're all comfortable with the idea of arriving at that answer? Okay. This one is slightly more complicated. How many half-lives have elapsed to yield a sample with 125 atoms of carbon-14 and 375 atoms of nitrogen-14? What you have to understand before you can start this problem is that nitrogen-14 is the product of decay. So that means we still have 125 radioactive things, and we have 375 things that used to be radioactive. So how many radioactive things did we start with?
500 atoms.
So we started with 500 radioactive atoms. We all see how we got there? Now what do? Scratch your head, poke your partner. Those are both options. Dominic doesn't want you to do either. See what happens when I sit near you? You end up being the one that gets picked on the whole hour. What's the next step?
Next step is finding what percent of the atoms are still radioactive.
So we have 125 that are still radioactive, and we had 500 that used to be radioactive. So we know that 25% of them are radioactive. Yep.
How did we know that N14 wasn't radioactive?
You will get a table that tells you the product of every radioactive one. With me? So from here, we have to figure out, they want to know how many half-lives. I have 25% of the sample left. Again, two choices. Choice number one. Oh, no. I didn't want that line the whole way. Now some of you are like, but I don't know how to solve for x. I don't know the mathematical function. How many of you are like, yeah, we don't know how to do this yet? Really? You all know how to do this? What's the mathematical function called that does this? Listen, first and sixth hour, we're like, hey, no, if this, yeah, it works out to be a perfect square, so I can do this, but if it weren't, I can't. It is indeed.
It's like log power.
Mhm.
Like if it was 2 log base 2 is going to be 7 to log 7 by 4.
So you all can do it? I've got like 4 yeses and 3 likes, oh, heck no's. And then a lot of this. All right, let's just opt for the oh, heck no. Can we do that? Here's what we'll do. How about if I did that instead?
That's a lie.
How many of you are like, duh, x is 2?
Oh, wait, is this
This is the moment that my mother would look at me and say, I see, said the blind man as he picked up his hammer and saw. Oh, Mom. No. That's option number 1. For those of you who just had that ding, you may go for that one. Works for you. For those of you who are still fumbling and clapping because you're hoping it's actually like a clapper light, you can do it this way. It's the graph. The exact same graph. This is craziness.
How many times did you draw that graph?
More than you want to know. I was just spinning in the chair when you guys showed up. There's a reason for it. Other than the fact I'm like massively easily entertained. But that does give me a great deal of comfort that you guys may recognize there's a repeating theme here. Good. Knowing that's true, if it is 1/4, so it's 0.25, I find it on the graph, 0.25, trace it over, find it down, voila. Did I arrive at the same answer? Are you all aware there are 2 ways to solve all of these problems? Fantastic.
Great.
100%. Written as a number, as a decimal number, what is it?
1.
As a fraction. 50% as a decimal. As a fraction.
1/2.
1/4.
Point 125.
0.625.
160.
Why is it at 300
To point out that you have to remember there's a 0 there.
Yeah, guys. 0.0131. That's a lost number.
That's as far as you're ever going to have to go with those graphs. Why? Because this one corresponds to a x equals 0, correct? You agree x equals 0?
Yeah.
And the next one corresponds to x equals,
1,
and the next one corresponds to x equals,
2,
and the next one,
3,
and
4,
fabulous, the last one. There are some people, man. And we never go past 5 half-lives, right? Because then the radioactive isotope is completely useless. I just wanted to make sure that we all were, we brushed off the fraction to decimal thing, because sometimes that's unpleasant. But hey, you're all going to have a calculator for the test that's not your iPad. So you'll easily be able to, just put it in your calculator, right? Oh, good.
Wait, do we need to bring a calculator? Can we use graph calculator?
Yeah, you can use a graphing calculator. That I don't care about.
Wait, we have to bring one?
Wait, when do we need the calculator for that?
You'll need it for your chapter test. Probably looking at probably Tuesday the 19th. I think that's the
Okay, so
19th.
you'll give us some fair warning.
20, I think Tuesday's the 20th. Oh yeah, you'll get your week's warning. Okay. You're all staring at, this thing. First thing you need to do. You got those colors, right?
Do you recommend matching our colors to yours?
No, just whatever you're happy with.
Okay. Okay, wait, which one is gonna be the biggest space? Cause I gotta skip that.
The left will be the biggest space.
I know, I'm gonna put
Wait, do you want us to do that right now?
Mm-hmm. Oh. Poor tellurium. There we go.
I love that one. That's my favorite because like copper and tellurium spell cute.
That they do. First thing you are going to color in are these, and I just colored them in for you because, quite frankly, they are of biologically not a great deal of significance. So we just kind of color them in and then promptly forget about them. They're called the metalloids.
You want us to do the GE one?
Wrong button. I like to call this particular part of what we learn here in chemistry anatomy of the periodic table, because the periodic table is so awesome that when you learn all of its secrets, you will know all kinds of crazy shortcuts to things that you will never need notes for. You'll never need a note card. You'll never need a cheat sheet. If you have a periodic table, which you will get on every test you have in chemistry, you automatically have all kinds of answers if you understand the tool that you've been given. So we learn its anatomy, its basic parts, and how to interpret it, and I'm going to teach you some stuff about the American system that's no longer taught anymore because, well, it just makes more sense. Why it's not taught anymore, well, that's just dumb. So I'll teach you the shortcuts, the American way. But while you guys are doing this, I want you to take a moment to discuss with your partners which side you think are metals and which side you think are the non-metals. Ready, set, go. Okay. Are the ones that I colored in the pieces of evidence you used with your partner to determine which were metals and which were non-metals?
Yes.
So I might have colored in something like, oh, I don't know, gold, silver, tin, iron, copper, titanium, platinum. And you're like, those things obviously are metal, right? So how many of you are like, yes, I will tell you that these, clearly by process of just looking at the ones you colored in, these must be metals. And now some of you are like, and things that are non-metal. I know that carbon's not metal. But I know that hydrogen's not metal. I know oxygen's not a metal. I think that chlorine's not a metal. And I'm confident none of these are metal. Was that a similar discussion to what you had with your partner? Yeah. Here's the secret, though. All of these are non-metal. As well as our friend hydrogen. That's not that tricky. You're like, yeah, okay, I'm fine with that. What most of you will dislike, all of these over here are metal. So lithium, sodium, potassium, calcium, magnesium, etc. Those are all metal. So now you may color those in, making sure you know that these are metals and these are non-metals. And I'm going to add one more color to mine just because I can. As you are coloring these in, that last column with helium at the top of it, draw a crown on them. You could color those the same color as the metals if you were inclined to color. My crown is going to have gemstones in it. You can. Truthfully, we pretty much always ignore the bottom because biologically they don't really do a whole lot for us. The only one you guys are really familiar with is uranium. The rest of them, even in chemistry, you'll ignore most of those. So if you've crowned that last column, we've crowned them because we call them the noble gases. And again, truthfully, noble gases is really a very accurate name because, well, like most nobility, they're essentially useless. They really don't do anything. Unless you like electrocute them, and then they'd probably do something fascinating. And that's true for the noble gases as well. This is not my suggestion to go electrocute nobility. That would be probably an arrestable offense. About that American system thing that I was telling you about. Chemists like to number the periodic table because it, well, makes it a lot easier to talk about things. Instead of me being like, oh, find the column that contains carbon. Well, then you have to go on like this goose chase for it, right? But if I said find the fourth column, you'd be like, oh, easy peasy lemon squeezy. So here's what we do. This first column is column 1. 2, skip a few, 3, God bless you, 4, 5, 6, 7, and 8. This is the American numbering system. That skip a few thing, that's how we do it stateside. The International Union of Pure and Applied Chemists do not do it that way. They just number it straight across 1 through 18. And what's really unfortunate about doing that is you lose a super important shortcut that the periodic table provides for you. And I don't want to lose that shortcut because me, lazy. I like shortcuts, right? Anything that makes something easier to remember, probably worth doing. So we're going to number it this way because it's going to help us learn a little bit more about the periodic table. In order to learn those things, though, we have to think about atoms and their basic shape. So what can you tell me about the basic structure of an atom? We all know it because it's where we started, right?
Nucleus and electron.
All right, it's made of a nucleus and an electron cloud. And what do we stash in the nucleus? Protons and neutrons. And what's chilling in the electron cloud?
Electrons.
Fabulous. Hey, how many of you guys have built a bookshelf before?
Built a bookshelf.
Yeah. You know, go to IKEA. You spend forever going through the showroom because it's like a maze.
Well, sort of a bookshelf.
And then you're just really irritated and angry. Then you get home and you have those set of instructions that don't actually have words on them. So then you just end up mad. But you did get that frozen yogurt at the end. So you're like sort of okay. And then you go to put things on your bookshelf. When you put things on your bookshelf, where do you start?
The bottom. If you start at the top, it's going to top over.
You got it, friend. IKEA just had to recall a whole bunch of toddlers' dressers, right? Because they were crushing toddlers. See? Crushing toddlers is never a good thing. Whoa. No matter how annoying a toddler is, we're never allowed to crush them. Just so we're all clear. The physics of the thing. Anytime you read the instructions, if IKEA bothered to actually provide words with their instructions, anytime you read the instructions, it would tell you to start filling the shelves at the bottom. And, you know, it says some nonsense tomfoolery about being top heavy and you don't want it to topple over. You want the physics of the thing? Higher off the ground you get, the more potential energy you have, right? You put that much weight up that high with all that potential energy with nothing below it, it's going to be off balance. Insert toddler here who is ill-behaved, who sees the bookshelf and is like, a ladder, and they start climbing it because you can't trust children and don't pretend you didn't try it when you were a toddler. Some of you are like, me? Never. Mm-hmm. As soon as you do that, the things with that much potential energy at the top, potential energy turns into kinetic energy, and then bookshelf topples over. Agreed? So whenever we fill shelves, we always start at the shelf with the lowest potential energy and work our way up. This is simple physics. I know it's simple physics because I know it. Physics, not really my bag. Now what I do? I know enough to not get toppled or by a bookshelf, right? I know how to not get squished. I know how to not get in a car accident, and that's about the extent of my physics. Simple physics is the exact same way an atom works. So when we look at an atom, the atom has those parts. Only column on the periodic table who has a completely full last shelf are the noble gases. To fill a shelf on the periodic table, you need 8 electrons. The noble gases have 8. Conveniently, it's column 8. Wonder how that works out.
Oh my.
Silly
Oh
Americans.
my gosh.
So the only one to have a full outer shell are the noble gases, which is why we said the noble gases do nothing. They're completely stable. They don't have to do anything because they have what we call a complete valence shell. A complete valence shell is also known as a complete octet. Absolutely. You must know that. So 8, octet, right? That means that you have 8 electrons in your outermost energy level. And the only column on the periodic table to have 8 electrons in their outermost energy level are the noble gases. That's why we call them inert. It means non-reactive.
If the closer you get to the nucleus, the stronger the pull is, how come there are only 2 electrons in that first shell?
Don't necessarily consider it the stronger the pull is. The strong force is what holds the atom together. But it's not that... The farther away you get, the easier it is to lose electrons. But it doesn't... I don't know how to describe it. It's a lot of really complicated physics. Trying to figure out how to do it without math. Let me think of a way to do it without the math, and then I will get back to you.
Okay, so about the periodic table, the skipped ones, if you ask us to find one of those,
I won't.
okay.
So the question is, will I ever have to know how many valence electrons there are in the 1-2 skip a few section, right? The skip a few section, I'm not going to ask you about. Will Mrs. Carl next year? You betcha. But here, I'm not worried about those. Here, I just want you to know anybody in the columns we've labeled. The column number is the number of valence electrons it has. So in column 1, it has 1 valence electron. Column 2 has 2. Column 3 has 3. Column 4 has 4. 5 has 5. 6 has 6. 7 has 7. And 8 has 8.
What was the balance is how much is on the outside?
And the last shelf. So if we're still using our bookshelf analogy, a bookshelf could hold 8 books. If we're trying to fill the last shelf, let's draw a bookshelf. So everyone on the periodic table that does react is going to do so in order to make sure they have a full 8. So if you only have 1 valence electron, are you going to give away your electron or go find 7 more?
Give it away.
If you are a giver, we all have friends like that who just constantly give. How would you describe their personality? Selfless, kind. They're pretty positive people.
Hey.
How about the one in the next column who's likely to give away 2 things?
Negative.
They're twice as positive.
BBC is Anna Crandall and Sarah Knowles, and we have a late day announcement. Tomorrow at 7 p.m. football game is a spirit event.
Check everything out. It would help us greatly, teachers, if you can turn on all
I'm such a good drawer. Here we go. Oh, it's a bookshelf. Here's 8 books. There are 8 books. There's 1 book. Is it going to be easier for me to find 7 more books to fill the rest of this shelf? Or is it going to be easier for me to be like, you know what, that last book, we don't need it. We get rid of the last book. Now, what if there are 2 on that shelf? Easier to get 6 more or just get rid of 2? 3. 4.
Oh, fine.
Oh dear.
Get your,
Let's skip 4. 5. Get 3 more. 6. 7. Get 1 more. So let's just represent the nucleus with a big fat N. Because that way I don't have to draw all these protons and neutrons because I'm feeling a little bit lazy. This part you don't necessarily have to write so long as you pay close attention to why it works the way it works. Closest to the nucleus is like being closest to the ground. In fact, physicists and chemists call that the ground state. So if we're going back to thinking about our bookshelf, we always start filling the shelves closest to the ground.
so it's like the nucleus has its own gravitational pull.
It's called the strong force, which is like a really terrible name for it, right? It's strong force, but that's what they call it. There's also 2 weak forces. Physicists. The biologists would have made up better names. So we start at the ground, the lowest energy level. And we've got all of these electrons that we need to store in the electron cloud. And we're going to start at the least amount of energy, fill the shelf, and then move to the next shelf, just like you would if you were properly filling a bookshelf. Now some of you are like, but then you look at the bookshelf and it looks weird because you got like this one empty shelf up at the top and then you've got like all these full shelves at the bottom. Well, fill the top shelf with light chotch like a stuffed animal, okay? Get over it. That's the proper way to fill a bookshelf. Yeah.
I suggest putting pictures up there.
Pictures would be a good choice. I also truly, as somebody who appreciates not getting, squished by things, just bolt the bookshelf to the wall. Truthfully.
Then you can't move your furniture.
Correct.
Now you have a hole in the wall.
I'm just trying to prevent future generations from being squashed.
So, yeah.
Put the books on the bottom shelf and we don't have a problem. And that's exactly what atoms are going to do. They're going to put electrons on the bottom shelf. And the Bohr model is going to show us that with like that horrendous Jimmy Neutron model, right? So we're going to have to rely on it because it's what we've got. But once that one is full, we move up to the next one. And then we continue to move farther and farther away from the nucleus. The last shelf that contains an electron is called the valence shell. That's the last one on the farthest outside away from the nucleus. You guys recognize, just making sure we understand why it's possible, that you might not fill a bookshelf, right? There could be like a partially full bookshelf.
If you're not into reading that much.
Well, even if you are and you just buy enough bookshelves, you're going to have a partially full shelf. Now, as far as physics goes, we also should recognize that physics suggests that the most stable bookshelf is one that is completely full. It is less unbalanced, it is less likely to topple over. We can apply that law to chemistry, that understanding, and we can say that it is more favorable for any atom to have a completely full shell than it is to have one that's partially full. We always aim for full. Full is better. Problem.